Welcome to Lab 5, the falling slinky. The purpose of this lab is to model the motion of a stretched slinky dropped from static equilibrium. In order to do this, I recorded a slinky falling. I obtained real data from analysis of the video with Tracker. Then I created two models using point particle systems that are similar to the ones used in Lab 2. The first model considers only gravity acting on the system. The second model, gravity and drag force acting on the system. The results I got show that the second model that takes into account drag force is more accurate since the mass of the object is not compressed, creating air resistance. However, there are still some discrepancies with the observed motion due to mistakes when determining the points of mass. Also, the fact that we are considering the slinky as a point particle system affects the results since we are not considering the stretch of the coils as it falls. I will discuss later the differences if the slinky is treated as a multiparticle system. The fundamental principle used in this lab is Newton's second law, since it gives us a way to predict the motion of the slinky by using changing velocity and the net force. At the beginning, the velocity is zero, since it is thrown from rest, and the center of the mass of the slinky accelerates downward. The mass of the slinky is 0.227 kilograms. The forces involved are the drag force and the gravity. The gravitational force acts downwards, and the drag force acts upward contrary to the movement. In Tracker, I set the coordinate system to be my positive x-axis to the right and the positive y-axis up. The length of the slinky was used as the length of the calibration stick, which is 1.20 meters. The points of mass were determined in each frame at the 40th coil, since it is the middle of the slinky. The picture obtained from Tracker shows that the moment where the slinky is totally compressed and starts collapsing to the ground. You can see this instant mark in the graph also obtained from Tracker. As you can see, after this moment the object starts falling exponentially. The first model done with Python only considers the weight force acting on the system, which is only the slinky. As you can see, the modeled motion starts below the origin because it was considered from the middle of the slinky. The yellow arrow represents the weight force, which was determined by the formula W equals negative mass of the ball times gravitational constants times J hat, and the F net is equal only to the weight force. This suggests that there must be another force acting on the system. The second model considers weight force and drag force. The drag force was determined by B times the magnitude of the velocity squared times J hat. B is a constant determined with the code and is equal to 2.47. The net force is the weight force plus the drag force. As you can see in the model motion, the drag force is represented by the blue arrow and is going up, and the weight force is represented by the yellow arrow and is going down, just as expected. When comparing the motion predicted by the two models with the observed motion, we can see that the second model that takes into account the drag force does a better job predicting the motion. Even though it is not completely accurate, it gets closer to the observed motion than the first model. The bottom of our model slinky does not stay stationary just like in the video we recorded because we are treating it as a point particle system. This means that we are only modeling the center of mass of the slinky. The model correctly predicts the motion of the center of mass of the slinky accelerating downwards. On the other hand, what if we model the slinky as a multiparticle system? We release the slinky and the contact force exerted by the hand propagating down, changing the stretch of the first coils of the slinky. One coil after the other begins to collapse down, with the coils below the leading edge of this collapse remaining motionless. The bottom of the slinky appears to levitate in the air, remaining in the same spot until the leading edge of the collapsing portion of the slinky reaches the bottom, at which point the whole slinky falls to earth in a collapsed coil. We are changing something at the top, and it takes a period of time for the bottom to know it is changing. The signal has to propagate from top to bottom. The center of mass starts accelerating down. If we model a multiparticle system, then the bottom of our model slinky will stay stationary just like in the video. Thank you.